We're live.
All right, we are live, folks. Time to start. All right. Welcome, everyone, to this meeting of the Warren Astronomical Society. We are at Macomb Community College, South Campus right now. I'm Bob Tremblay, your president. Let's do a roll call. Let's start with me. I'm Bob Tremblay, your president. Dale? Let's do this.
I am Adrian Bradley, current treasurer. We're going.
Dale Parton, first vice president.
So, Mike.
Richard Mansky, where am I, by the way? And I'm here.
Hey.
Oh, there you go. Eduardo Saluso, just a number.
Hi there. That's somebody new.
Observatory chair.
Right
there.
All right. The attendance roll call. We have a rainy day here. Hopefully that's well, actually, this is better attendance than we had last time. So maybe the rain isn't doing it, but we've had rain the last 3 times we've come here. So we have a first timer. Hi. How'd you hear about us? Awesome. Well, that has certainly made us enough new members. Awesome. So you can join or renew your membership with that man right there via PayPal or on our website. Our 2024 astrophoto calendars are here in attendance, and you can get them for $15. Beautiful photos by our members. Get them while they last. Our awards banquet is being held at the Ukrainian Cultural Center, December 11th from 6 to 11 p.m. The price is $35 pre-reg, $40 at the door. Check our PayPal, or I believe you can just pay Adrian right there if you're here. John Blum, our former president and member of most, if not all, the astronomy clubs in southeastern Michigan, will be our keynote speaker. And thanks to Dale Parton for getting him, and thanks to Mark Kezier again for all his efforts in organizing this and finding the venue and stuff. Our elections are being held. Our next meeting in November, Cranbrook. We have several board members who are being term limited out. If you're interested in helping the society or have a nomination for someone you think should help the society, get with Mark Kezier, who is our organizing committee, and we need your help. So the Metro Parks have one remaining event, and this is likely to be a big one. It is this Saturday, the 21st, at Stony Creek Metro Park. And they're going to do pretty much a repeat at what they did at the Perseids event this summer. They're going to have a big tent and the red rope lighting. Hopefully we can get some telescopes out there, or at least a telescope. McConnie and I will be behind the WASP table with our really cool new banners and stuff. And so that is this Saturday. If you can make it, please do it. Adrian. Stony Creek. I will get you it is one of the campgrounds, and I will give you the name for that. Yeah, that's going to be the same one. Yeah.
I can't make it up.
So Adrian, you want to tell about this event on the 28th? For those that are interested, there will be a downtown Brighton, welcome back to downtown Brighton event being run by Denise Murray. Jeff, I've put you in contact. All of you are invited to come out if you would like. The event is from 1 p.m. to 6 p.m. And what it is she wants some astronomers to help give an astronomy type theme with it. It's Hunter's Moon. So looking for any and all things astronomy, talking about the moon, talking about other astronomical things. I don't know if she was in touch with you when you mentioned spaceship. She got pretty giddy about that. The spaceship will be there. I'll be there sharing some images. and or working with one of the couple of telescopes they have. If you want to bring the big knob and make everybody in Brighton go to it to look at views of the moon, that's something she would be open to.
Big dot is not transportable.
Then it would have to be your own big knob.
Give it the one that take, I mean, we don't have access to some of the smaller big dots.
Okay,
So 13.
yeah.
Or 13.
So,
Take that out, no problem. Before we do it.
well, and I do have a truck. I would have to get all sorts of things out of that truck, but like bowling equipment, don't really need it anyway, can't bowl. So, um, ran into my buddy at the bowling center who's the professional that's been trying to help me. I wanted to be a professional bowler at one time. And then I found astronomy during COVID and photography. And now my money goes into other hobbies. So join us. If you would like, if you are interested, stop by and see me and I'll write down your email on either primitive napkin or tap it into my phone and I will send an email to the organizer, Denise Murray, and include your name.
I can get with you and send out an email blast to the membership.
Okay, let's do that.
Yeah,
Let's do that. And then here, because I see we have a few that have logged in online. Bob was able to set it up himself. Congratulations, Bob. And finally,
Hey, they gave me absolutely no troubles. I'm waiting for the other shoe to drop.
so that's if I touch this button.
Yeah.
So if interested, come see me or wait until the
Email blast goes out.
again, it's the 28th, anytime between 1 p.m. and 6 p.m. That's a Saturday. Excuse me. Full moon, hunter's moon. We've been told we can see because moonrise is somewhere around 6:30, 6:45. What's the use of having an event if it ends when the moon actually rises? Yes. And if it happens to be a nice enough day, solar scopes are a possibility. Let them see the sun safely. There will be the idea is brews and views. So there will be kids to start. The event may or may not be more targeted to adults who are coming out of brews. It could be a fun time. If you bring your equipment, please be careful to watch over it and make sure things aren't going bad or worse. But you're able to stay somewhere between 1 and 6 or afterwards as long as you would like. We don't know when someone stays till 2 in the morning. It's probably going to be real late at that point. So we'll find out. It's a whole public downtown. There is a public, yes. Yeah, there is a public park there. It's like a pond. I forgot what they call it, but there will be events going on in their part of town. At least that's the intent. And the more astronomers we have, the more astronomy setups we could have in front of some of these businesses. The goal was to revitalize some of the businesses, and Denise's idea was let's throw an astronomy team behind it and get people interested that way. So it becomes kind of a unique thing. It's not just everyone walking around and drinking. It's learn something about astronomy. So any other questions before I turn it back over to Bob? And if you do have questions, you can always come see me. Most of those questions answered after we contact them to let her know how many more are interested. And if you're able to be here, fortunately, Dale, we're gonna miss you, but thank you for at least being interested. And so that's the 28th of October, and the what was the other event? When was that?
Metro Park?
Yeah,
Saturday.
that's this Saturday coming up. Okay, so there's just making sure there's no conflict. So, all right, that's it. I'll be probably back up later, but All right, so for an officer's report, I finished editing a podcast today. Brother Guy interviewed Charles Bolden Jr. Now, I mentioned this in the intro to the podcast, that the only thing I knew about Charles Bolden Jr. was that he was the NASA administrator back in 2013 when the Chelyabinsk impact happened, and he was talking with Congress, and they asked him, what could we do if we discovered an asteroid coming in toward a U.S. city and it had only 2 weeks? His response was pray. And so I'm glad with the DART mission and stuff like that our asteroid defense has taken at least some strides. But so yeah, so that was about the extent of my knowledge of him. But he's a retired major general in the Marine Corps, and he was a shuttle astronaut. He was on the mission that deployed the Hubble. And I'm like, why did I not know that? But Brother Guy talked with him, and it was a fascinating interview, and it told about his rise from childhood, about him wanting to go into the Marines and stuff like that. And it was a very it was a very cool story. So I'm very glad I got that done and up today. So our first VP, Dale Parton, says we have presentations scheduled through next spring, and we need short presentations. If you have any ideas, be it a space mission or some astronomy news that you find interesting and you'd like to talk about, let Dale Parton know. Anything else to add, Dale? There you go. Okay. So, Jeff, observatory, you got anything to talk about? Oh, geez. Our next star party is October 28th.
Fourth Saturday, as usual, I'm going to drag the spaceship from Brighton to Stargate, so I might be a little late, but you can do both things. Just one no. Oh, sorry. Yeah, not this weekend. 28th, same as the Brighton event. Not this Saturday, next Saturday. I'm packing up at 6. I'm heading right to Stargate, so I'll be there. In other observatory news, I don't remember how our last open house went. It's been too long. My memory is like 2 weeks tops.
You're not even 60 yet.
I just got too much to put in there. I need another RAM cartridge. Mark Kitzer and I were out at the observatory yesterday. We shuffled some stuff around. So the Dob shed has, in my time in the club, never looked so good. You can actually get to all of the telescopes. I know. So this is a unique period in history where
Contemporary.
if you come to Stargate on Saturday and you want to use one of our smaller Dobsonian telescopes, you can actually get to it. And we can bring it out and you can run it. We want more people that know how to run these scopes.
What company was the Big Nest?
The Big Nest is gone. It's gone. Did you want it? We didn't think to say that. The seas are gone. It's all swept out. It's beautiful in there. I have photos, but maybe next time. All the credit goes to Mark. Heavy lifting. We just decided when we were going to be there. Now, the other thing is I have several scopes that I want to give to a youth of some sort. I don't think there are any scopes that y'all would be interested in. They're small equatorials in various states, some good, some not as good. But like if you're 13, it'd be an awesome first scope. Put the word out. I think we have 3 of them in that kind of category. You can argue with me, and maybe the board will. I don't think they make good loaner scopes. I just want them to go to a home.
In other words, go away.
Yeah. But no, for a teenager that maybe, doesn't have the money or just wants to like try it out, borrow it. And if you never bring it back, more power to you. I don't know. I started off with a scope like that. I don't have one anymore, but like that's what you start with, right?
What sort of mountain on those?
They're all equatorials. No. Yeah, there's an Orion, there's Pasco, and
There's an old. The mouth has to be like this, right?
Oh, I mean, they're fine. They're fine.
Yeah, looking at a mouth that I could use with my solar scope in case someone else. The solar scope I have is actually the lowbrow solar
All
scope.
right, get at me at the break because I probably have a mount fitting somewhere.
Yeah.
So the other thing out there in internet land, we also have scopes that I would like to sell. So I haven't spoken to the board yet about what we might be wanting to ask for them, but I have an 8-inch Meade, a 10-inch Meade, a 12-inch Meade, 5-inch Bosch and Lomb, an 8-inch Celestron, and we don't really need any of them. Like some of them have never gotten out of the box. Like they're all there. Some of them have some issues. Some of them don't. If you're interested at all, at some point they'll go up in the WASP. That is what is occupying the trailer right now. That is why the Dob is not mobile, because our trailer is full of all the stuff that I want to get rid of. We also have a pop-up like canopy tent mesh canopy tent thing. It's not nice like the new ones that go up in 10 seconds. It's kind of like you got to assemble it. But if it's something that you're interested in for any reason, it is yours free.
Free.
Right. And then lastly, internet people might not be. Oh, two things. No one else made it out to the plane wave event. Y'all missed out. It was pretty cool. Look at this shirt I got. Oh yeah. Jealousy is a really good scratch and dent. What? Scratch and dent sales? No, there's not. Their cheapest scope is like
Yeah.
way.
My buddy likes to say, what, cosmetically defective or otherwise unmerchandisable, but still optically correct. There you go.
Plane Wave is pretty amazing. They impressed me with how, I mean, they got a bunch of people to come out. They got that small town charm. Like, man, Adrian loves them. So it's a pretty cool event. Yeah, you should have been there. You'd have been a kid.
I was there before. They were here grand opening.
But yeah. Look at this t-shirt. Oh,
Wow.
so lastly, yes.
So if I recall correctly, Plane Wave makes stuff from 12.5 inch up to 1 meter.
I think they're working on a 1 or a 1.5 meter. I don't know if it's like out yet, but yeah.
That like 6 figures.
Oh yeah. They're like universities. They specialize in like.
I'll say at least 7 figures.
7 figures.
$4 million, I think, for their month.
So lastly, we have, these are like slate tiles. It is the first man and woman in the US and Soviet Union. If you're interested, let me know. I would like to not.
Here, can you give me one for the?
Yeah. They were made by an artist for some reason, and then they went to this person. That person didn't know what to do with them. I was the only astronomy person they knew, so then they came to me. I don't know what to do with them. No, this is no US. This is Mercury. Alan Ship. Yeah, I say first orbit is a little bit first, but yeah, Yuri, right?
So that is sounding right. Sounding right.
I have no idea how these were made. I don't know if they're chemically etched, if they're laser etched, if they're printed on there. And then this one, I actually don't recall the name. This is like good trivia. First Soviet woman. First woman.
Yeah, Valentina Tereshkova. Trying to think of the name because that's the name they use in Kerbal Space Program. Yep. All right. So, Treasurer Adrian, how much money we got in the bank?
We're at 25,000 in the bank.
Nice. It's down from 30 something.
Yeah.
Amazing. Is it still going up? I'll start worrying about it when it gets to 10. So, Mark, anything to speak about? Nope. Stuff's in the WASP.
Outreach. Kevin is not here. I've gone through most of that stuff anyway, and so is Adrian and I. Pardon me? Yes.
Regional conference is coming up. The website is,
Oh, really?
yeah, astrophysics.org.
All right, I'll put that at the break, which is going to be happening fairly soon. So, let's see, Dale. The newsletter is up. Anything else to say? You, Dale.
Okay.
Dale.
Not much else. Otherwise, the WASP is up online. We're still on the calendars. Everything's moving along nicely. November's on its way.
All right. All right. So, astronomy in the news. Psyche mission launched. I missed it totally. Don't know why. I should have done the asteroid mission. I should have seen that, but oh well. I've been busy this week. Adrian, you went to the Okie Tech Star Party. Do you have anything to say about that? Yes. Yeah, I have other ones. Anyone been to any other astronomy events recently?
This is where we start to share images. Let's see, where is Zoom?
No, here.
Yep. Over here, share screen. Yes, there's a screen right there. Okay, so things we do at yeah, well, yeah, we can't see it here. That's because I haven't put the picture up there. Let's go and do this. Okay. So prior to going to Okie Tech, I spent time.
You're sharing this screen though. You need to share.
I'm sharing. Wait.
Yeah,
it was down
here, and you shared.
in here.
Zoom can't.
Oh, Zoom can't see it. Oh, that's great. Okay. So we'll stop the share. Share the screen. This one.
Yeah.
I guess I'll just share that.
Yeah.
Okay.
That works.
Now everybody should be able to see. All right. Kind of goes into an observing report. So going out to Port Crescent State Park where we do sunset and birding at the same time. Sun goes down. This peculiar thing happens where it looks like it's melting into the water.
That's weird.
That's an interesting thing. And then the moon came up, and it's a challenge to get the moon and see it with any detail the way that your eyes actually see it as it's getting darker. So that's a challenge that I always take on. And of course, as it got full, I took pictures. That's the blue moon. We all remember that it was not really blue, but in Photoshop you can do that. Then I went to Okie Tech's and we stayed at Black Mesa. And the first night, this is where, had I brought your lens, Dale, I would have tried a few shots with it and you would have seen something similar to this. Now, where it's dark, Bortle 1, you start seeing the Milky Way, your camera starts seeing it, and it's nautical twilight, not astronomical twilight, nautical twilight, and the Milky Way starts coming out. That gives you an idea that you're in a pretty dark place when you can start seeing it that way. All of these images here, past astronomical twilight, there's a light dome here, and some of us you go out to a real dark place, and it's flat. But we figured that was Oklahoma, which is some small town in the distance. We also figure it might be like a feeder, whatever building on a farm where it's really bright. But those are the light domes. Everything else, as you can tell, goes straight to the horizon.
How long was that exposure?
This was maybe a 4-minute exposure. And then combined with like a 4-minute ground exposure. And so this was one of the only, there were 2 good nights in the area. You see some of this, because you're south and west, you see things like this. The cat's paw, the lobster claw didn't come out so well in this one. The prawn didn't come out, but you can see some of the nebulosity here. The entire bit of scorpion is above horizon, which doesn't happen unless you go to you shoot at a specific location and you've got a low enough horizon. That's, I forget, I think NGC 6231, which those are things that just plain disappear. This one had a little more of the Rho Fuyuki complex. So I took a few of those pictures. You turn around, you get just as impressive stuff. That's camp where we stayed. So now let's go. There's the actual, if you go to Okie-Tex, this is where you actually are. Camp Billy Joe. Same thing was happening. This was day 2. There's a glow from sunset, nautical twilight. There are some places in Michigan, you're lucky when it's astronomical darkness and you get a Milky Way that looks like this. So, of course, what do? We shoot Milky Way. I tried to shoot this to be more of a true to what you see with your eyes. There's a little more detail here than what you see, but you see the dale, you've seen it. Anyone that's been to a dark area knows that when you're looking up at the Milky Way, this is what you see. You know, give or take a little bit of the detail. You do see M8 plain as day. You see the Sagittarius star cloud, and if you're really good with your visual observing, you will see M16 and M17. You'll see some of the areas there. You'll see these dust lanes, and you'll see some of this region. It may not have quite the detail here. This is the region where things like the pipe and there's other dark nebula that basically make up that region of the Milky Way. And over there, it's just a lot easier to see. This just gives you an idea of how many stars there are. And this part of the Milky Way, that's Andromeda. There's proof that I do look through a telescope every now and then, Jeff. The Milky Way is my backdrop, and some cool photos in a larger focal length. And this one, this is a good representative, even with the Milky Way, the core setting. There's still so much more to see out there. A lot of imagers go to the star party. Well, that was the last day. It was good out there, and that was the weather the rest of the time. Lucky enough for me, storm was moving south, was over here. So I ended up with some Milky Way against storm images that you don't normally see the two in the same field of view at the same time. We were there watching the storm as it went, and I have something that looks like bright in one of my photos, but I have not caught any sprites. And I didn't stay that long enough to see if I could catch sprites. I'm pretty sure there were some from this rather large storm, but there was a presentation on sprites at Okie-Tex that we went to not long after I took those photos. And what I learned is that all night I may have had a chance to catch sprites with some of my photos because there were plenty of 7-Ups, but what you wanted to drink out there was water. But the sprites, this storm very likely created sprites because it was huge, and you can see all the lightning strikes. There's a couple low brows that were just sitting there watching the storm, and I wanted the Milky Way and the storm to be in the same photo because it's just a rare time. Those two are normally not in the same picture. So Okie-Tex was pretty much like this the rest of the time. You saw some stars here and there, but it was just dark. That's what was left of, that. Yeah, remember this scene way back here. We took a picture of the that was before. And this is what happened to it most of the rest of the time. So real quick, well, yeah. So worked with stacking photos. It's interesting. This was dusk. That monstrosity over there ended up covering everything at night. So we went back to Denver, got the thin waxing crescent. This is Denver's Astronomical Society. This is their dark sky site. They have a pretty good dark sky site. This is what the Milky Way looks like there. I would say Denver, if it's it's either a very high Bortle 3 or a low Bortle 2 in terms of what you can see. The sky meter number already 21.3, 21.4. But I was getting 21.5 and 21.4 at Black Mesa. So the sky meters can do darkness aiming on the horizon, and toward the north, I was getting the 21.8s, 9s that you expect in Kenton, Oklahoma. But transparency is a big part of it too. And this was a transparent night, even though Colorado Springs is over here. And I don't know if I took any pictures with Denver. Denver is a huge, light polluted area. And so I didn't bother shooting in that direction. There's something over here too. I don't know what city it is, but shooting in Denver was fun. So came back home, full moon. And so we're trying to, this is sort of a short talk apparently, and trying to get the full moon with detail on it. So these are some of my attempts at showing that. So going back north, whenever you get a good image of the moon with some detail in it, you want to keep it. So I did that. And finally, we'll talk about capturing the eclipse. First contact, you might be able to see it on that screen. And
Did anybody see it? Go see it.
or go anywhere where you could see it.
No. My wife and I watched it on my phone while we were driving to pick up my granddaughter live.
Yeah.
Better than nothing, I guess.
What was the camera or where? Well, where was the camera? Sunset.
It was. I was watching NASA Live on YouTube. I'm not sure where they were.
So these were my creations, basically, with what little eclipse. We had sunspots. Neat little trick. If you don't have a filter, use cloud cover.
Did you have a solar filter for that, or was it?
Nope, the clouds were enough to use as a cloud cover to where,
Then you got the stuff.
and I got the sunspots. Yeah, and then you can get a reflection in water. Or you can point right at it and take a risk, which is what I did there. This was coming right out. That's why you see it glowing like this, because it was coming out.
Wow, that looks like it's sitting half in the clouds there. That's really cool.
Yeah. And then this one was what the eclipse looks like, even though there's tons of clouds. These were Caseville in the thumb. And there's the eclipsed sun peeking out. There are also, if we're lucky, no, but you can see some of the shadows. If you were able to zoom in further, you would notice that some of these shadows are actually the little crescents peeking through these trees. So if you get a chance to look at it.
You any ground photos of crescents?
No, I completely forgot, and I had every opportunity. So that is my observing report from Okie-Tex to Denver to the eclipse this past weekend. And now I will turn it over. The next eclipse or the next event, we're probably sometime this week try and get this Orion Rise again. This is Orion Set, but maybe go Orion Rise. I was out there and all of the water that you're seeing is actually water. It's rather interesting how different a location can look from summer to winter.
All right. Thank you, Adrian. And going down my list here, that's also our observing reports and yeah. Yes.
Can you do Psyche spacecraft separation? There should be a 19-second clip.
All right.
Did anyone else see Psyche nearly get obliterated by a piece of space junk?
What?
I can't find anyone talking about it, and it scared the Jesus out of me. Because you saw the space junk whiz by. It's plain as day.
It's surprising no one's.
I contacted Kate and asked them, I'm trying to get in touch.
All right. I'll share this.
Oh my camera. Because all my data is there to be able to figure out exactly how close it came based on shutter speeds and various technical things.
These lights, it's hard to really see.
Oh, sorry.
We're not getting stuff.
All right. So I'm running this video right now. This is on YouTube.
In the top right, space probably on the top right going, it's a deep space.
That is an awesome shot. It's like.
I saw that, yeah.
All right. There it is. In 14 seconds, you see it? Yeah.
Keep it in this is like it's big, like 9 feet tall. And so whatever that is, it's being illuminated by the same light that's illuminating the spacecraft. If you see the whole live stream, the spacecraft gets like maybe another 50 feet away, and it gets pretty, but that light is not, light in the world. Right there. Is that possibly sunlight, like a satellite 50 miles away was about?
It's not going so fast you can't see it, but it doesn't look like it's related to this spacecraft though.
Some online discussion, but I haven't been able to find it. But I mean, it's the light illuminating this from another section of the spacecraft here. Or is that sunlight?
Whoosh.
Sunlight. The thing that you're seeing, I believe, is
Wow, that was interesting.
kind of shadow in there.
It's definitely.
Like the spacecraft dips down over this one, and you can see it fading out of the light. So I don't believe it's being illuminated by the sun. Okay. Now, I mean, it doesn't kind of see this is the solar panel on the other side. It doesn't look like their sun is illuminated. I think they're on the other side of the planet.
Fortunately for all of us,
read it in less than on YouTube and go frame by frame.
Can you?
that's why.
So, you get the. I should be able to make that. Well,
I did not know you could do that.
it's smaller here, like the line is shorter, lengthens as it's going out there, which to me, like when you see the lines on the road, right? The ones that are near you, and they get shorter. So like this, to me, it looks like something. Within 50 meters.
Following the same trajectory, and it's in every frame. Yeah.
This is already, it's already outbound, right? So the second stage already boosted slightly into its. So So that was just some piece of debris in lower orbit. Yeah, it's gonna whiz by.
If it was just a random piece of debris, it would go by so fast. I mean, the relative speed between these two is what, a couple tens, maybe 100 miles an hour. But everything in space is going really fast compared to everything else in space. So, interesting controversy. Should have to hit Reddit on that. All right, so it is 7:40, so it is time for our snack break. Why don't we take a break and we'll do our main presentation back at 8 o'clock. No, yeah, it's 20 minutes. So that'll be 8 o'clock. So 20 minutes. So we'll take a bio break, go get a drink, go get a munchie. We're gonna do the same thing.
Pay for the banquet. I can't understand. I'm just saying, this is a good time for people. Hotel for down or the banquet.
Yes. I'm gonna give you a PayPal page, because when I left out the house, I meant to have a Astro room. I made sure Taylor legs within the truck, double check that. And Astro, we'll say hands, buddy. But you can still pay it when you PayPal. When you do bill. You pay $13.
Yeah, for a check for the last two, right?
Yeah. That's where the check does work. They have to have change. So we probably can't. If you're like Victor and you come longer than $100. Hey, I owe you. After some of these calendars, I'm going to PayPal. For an extra for and the March model. This is the winter. And I'm not a camera. Now, one hard thing to do is to capture stuff and your landscape around.
Hi there. How do you want to do this? Yeah, I'll have to swipe it off this, but that's fine.
We can just do that. Remember, I don't see all of the mouse.
All right, now, can we get you on Zoom on that thing?
Yeah, so if you give me the Zoom link, I can join it from my computer and then I'll start there.
Yeah, you know, click on it. Right. If we go to meetups, we can just click on the link. Like,
Yes. So this right here, that's the video. Settings.
All the difficult.
yeah, do the request to try and I can fix it.
See me in the link, maybe?
Yeah. Got Adrian's here. Yeah, it's a pain, I know, yeah. Get here. In Adrian's email here, I don't like this, but oh well. All right, so I am forwarding that to
Do you want to do Ethan Partington?
each.
Yeah, right there. That should be
Located in the box or.
Okay, we're getting presenter up on Zoom here. Get ready. You have a mouse or a clicker?
Yeah.
Right in front of my eyes. Yes, you do. This.
All right. Hey, how's it going? Yeah, good to see you too.
One of the things that
Doing well,
you
thanks.
brought up
All right, we are just a few minutes from our feature presentation tonight.
What's the Andromeda? In July this year.
We are returning in 2 minutes.
Oh, yeah. Because if you're listening to the thing where it's like, well, I got this one, but then what if that one gets lonely? So I got a second one, but then like, I mean, maybe those 2 points, so you get a third. And I mean, I've got 3, so I might as well just get the whole collection, right? I had one, and they're like, I think it's some of those. Oh, I got the one. We just got our 4 months together. Just get another case.
All right, what time is it? It is 1 minute warning. 1 minute warning. All right, everybody, get back to your seats, please. We're going to start up. Actually, I'm gonna stop it on this one. Mute. Start video. All right, there we are. All right, welcome back. We are. We are at the Warren Astronomical Society meeting in Macomb Community College South, and we are here for our. Hello, everybody. Our feature presentation.
Before I introduce our speaker, I would just like to say that we have our elections next month for club officers, and we still have no candidate for secretary, treasurer, or publications. So if you have any interest in any of those, please let us know. If you do publications, Dale Teamy has been doing that. He's willing to continue being the editor of the WASP, which means there isn't a whole lot of work to do for publications, but we just need people, okay? It's my pleasure to introduce Ethan Partington, who I've been chatting with. She's going to be finishing up her doctorate in physics at Wayne State University in June, approximately. Congratulations.
Thank you.
So they use multiple space and ground-based observatories to map the extreme environments of supermassive black holes and distant galaxies. I think at Wayne State, they must specialize in black holes and extreme situations like that.
Absolutely. All 3 of our astrophysicists are doing black holes or neutron stars. So
Yeah.
all compact objects all the time.
Yeah. Ethan also leads multiple black hole monitoring campaigns with NICER, a state-of-the-art X-ray observatory, which is on board the International Space Station. You haven't had a chance to get up there, right? This is remote observing, apparently.
It's work from home at its finest.
Also an invited speaker at NASA's 2022 Summer Science Workshop for NICER. And finally, Ethan is passionate about making the latest astronomical discoveries accessible, like here, to everyone, and gives free tours of the night sky at the Wayne State Planetarium. Topic tonight is demystifying black holes.
Ed, thank you so much for the lovely introduction, Dale. So my talk today is going to focus on the broad context of my research at Wayne State. There will be a couple of portions where we do dive into the specifics of my work and my findings. I'm very happy to discuss those during the Q&A as well. And to kind of encompass all of the things about black holes that I'd like to share, I'd like to go through kind of a few key questions. If I can get my presenter thing to work. All right, perfect. I woke up the computer. So first of all, what are black holes, right? We are all astronomers here. Everybody has some interest in the sky, in observing. Black holes are notoriously one of the hardest astronomical objects to actually observe. So we have learned all that we know about them really in the last several decades. It's been just nothing before that. So what are they? How do they form? How do we find them in the sky? And then what interesting science can we learn from them? So to start off, what is a black hole? We've all, I'm sure, seen art either in a movie like Interstellar or on the cover of a science magazine. There's this very classic picture of you get this sort of rainbow. I'm actually kind of dressed like a black hole today. You get this rainbow. You have this red low energy light that kind of extends in the outer arms of this disk. It looks a lot like Saturn's rings, right? You have this what's called an accretion disk. Basically, anytime you let something spin around an axis, similar to throwing pizza dough and spinning it, it's going to flatten out. That's why the solar system is flat. That's why Saturn's rings are flat. And that's why accretion disks are flat as well. And then you end up with the material heating up. So we go up the electromagnetic spectrum. You start to get thermal emission in the hotter optical colors. And then if your black hole is really, really hot, specifically around supermassive black holes, you can start to emit in the ultraviolet. And then you get this region that is a lot less strictly formed. It's called a corona, and it's going to just kind of hover around the event horizon. There's also this little light ring here called the photon sphere. And this is literally just light that is orbiting very, very close to the event horizon and is slowly spiraling away, similar to how the moon is very slowly spiraling away from the Earth. A little bit of that light will escape. So inside of where the disk is stable, this disk is formed through what we call viscous magnetohydrodynamic forces. So similar to when you pull a drain plug out of a bathtub and the water starts to swirl around, but it doesn't all go in immediately. This material here in the disk is made of some sort of nebula or poor star system that traveled too close to the black hole, got ripped apart by its tidal forces, and is now traveling towards the black hole. But much like the water in the drain, it's piling up. It's exhibiting this sort of viscous interaction that's stalling it out, making it slowly spiral inwards. And then that causes it to heat up. That's where we get that thermal emission from. Now we call it magnetohydrodynamic forces because black holes also are known to have extremely strong magnetic fields. Things like IXPE, the X-ray polarimetry observatory that has just now been publishing results over the past 2 to 3 years, have measured extreme polarization from emission around black holes, telling you that there's this insane amount of magnetic field strength. So as you get closer to the black hole, right, you have all these beautiful things that you can see from all that viscous magnetic interactions, and then you get nothing. And this is because light would have to be moving faster than it is physically possible to move in our universe in order to overcome the strong gravity of the black hole. We call this the event horizon. So there's not material in all of this event horizon sphere that we know of. There's just no light escaping. So to understand that, let's talk about what light is. I think light is really kind of beautiful. You have this oscillating electric field and this oscillating magnetic field, and they're running perpendicular to each other. And the it turns out when you have a variable electric field, that can induce a magnetism effect. And when you have a variable magnetic field, that can induce an electrical effect. So you end up with this kind of cosmic dance where the two of them are propelling each other throughout space. And it turns out that they are limited by how fast an electric field can travel through a vacuum. So this is the electric permittivity and the magnetic permeability of space. And it turns out that if you take a product of these, put it under a fraction and then square it, you get the speed of light. So this is about 671 million miles per hour, extraordinarily fast. For astronomers, we say it's 3 times 10 to the 8 meters per second, but that's the conversion I did for us because we're in America. So this oscillating light field, it will slow down if you put it in air. It'll slow down if you put it in water. That's why you get properties like refraction. But for the most part, space is a vacuum, so light travels at this pretty finite speed. And what that means is that when you put light in the presence of gravity, light is going to get affected by the curvature of space. And for most things, the gravity is super weak compared to the speed of light. The escape velocity is way lower than the speed of light. So we know on Earth, right, we have a pretty strong mass, right? We have a pretty dense, rocky world. And so the escape velocity is significant. You have to do these really dramatic rocket launches to get your material out into space, but light emanates. We've all seen the beautiful pale blue dot photo, I'm sure. Light escapes from Earth, no problem. And then intuitively, we can use the moon as a comparison, right? Gravity depends on the mass of the two objects that are attracted to one another. So the gravity on your surface is just directly dependent on the mass of whatever you're standing on, as well as the distance between you and your object. So the moon is less massive. It's also less dense. It's made of a lot of the similar material to the Earth's surface. It's got that kind of light, rocky crust and mantle material. So intuitively, we know that the moon's gravity is weaker because we see these little astronauts doing bunny hops whenever we observe astronauts on the moon. The moon's escape velocity is only about 5,000 miles per hour. Great for if you were going to kind of use it as a way station for space travel. Also highly reflective. We see light from the moon every day, except during the new moon. So light easily escapes from most objects, including our sun. The escape velocity of our sun is about 1 million miles per hour. And if we were to collapse the sun into the next most dense type of stellar material, that is a neutron star, light would still be able to escape. So who here is familiar with the neutron star? Okay, we've got a lot of people. As a refresher, and for those of you who might not be familiar, anytime you have a stellar object out in space, that object is in a war between its own internal pressure and its own gravity. So this sun was formed out of some nebula out in space about 5 billion years ago. Stars, as it turns out, can only be formed in these very cold molecular clouds. So you have to have this cold, dusty area of space that sort of coalesces under gravity. You get a little perturbation in your nebula, maybe from a nearby supernova explosion, maybe from a jet, from a black hole. This is kind of one of the major open areas of physics right now, is what channels lead to star formation. But some perturbation shocks the gas, compresses it. Now we have an area with slightly higher density that's going to have more gravity, and it starts to accrete, or material falls gravitationally onto it until you get enough mass to hopefully form a star. If you get about 1 solar mass of material, you're going to have this dramatic shock of hydrogen fusion that happens in the core. You have helium atoms or hydrogen atoms that are moving at millions of degrees Fahrenheit. They crash into each other near the speed of light and fuse into helium nuclei. So that's going to send out an immense amount of radiation pressure. Now, each individual photon of light takes about 1 million years to leave the core. Just statistical mechanics kind of dictates that it's going to take this random walk and get absorbed and re-emitted. But as it gets absorbed, it's heating up the plasma in the outer layers of the sun. So all of the light from the sun actually comes from a very tiny region in the center where the gravitational pressure is really high. And then through that absorption and re-emission and absorption and re-emission, all of that flux, or that light radiating outwards, will keep the star heated and prevent it from collapsing. Now, we have our radiation pressure, which is directed outwards, and that is in all directions from the core. Call that P radiation. And then you also have an internal pressure that is trying to keep the star collapsing in on itself. This is gravitational pressure. So the matter from all of these outer layers of the star are constantly pushing downwards. They're trying to accelerate towards that core. So you have this sort of equilibrium for most of the star's lifetime. Now, stars that are much more massive than our sun are going to continue to fuse heavier and heavier elements. They're going to fuse hydrogen into helium. Helium turns into carbon, oxygen, nitrogen, and then that material, it sort of forms like an onion-like structure, starts to fuse into heavy things like silicon. Eventually, silicon fuses into iron. Now, iron is thermodynamically impossible to fuse. It just takes too much energy to accelerate this highly dense nucleus. And so once the star starts building up iron, it will collapse inwards. It loses all of that radiation pressure. That's gone. It's not fusing anything in the core anymore. Collapses inwards, gravity totally dominates until it can find a new source of pressure. So a neutron star is one of the classes of objects that astronomers here at Wayne State study. This is all of the mass of the sun condensed into an area about the size of northern Detroit. So about 12 miles across. And here now, instead of being supported by the radiation pressure from your light, you're now supported by something called neutron degeneracy pressure. This is the densest pressure that you can get. This is the pressure that will support a solid surface on the densest materials in the universe. So this is the last stop before you become a black hole. This is just all of those neutrons literally like obeying the laws of atomic physics and not occupying the same area in space. So neutron stars, very, very dense, still they shine. We can still see them. And so their escape velocity is still not high enough to beat the speed of light, not a black hole. Now, what do we think the sun might need to be compressed in to become a black hole? This is where that area is so small that you would have to travel faster than the speed of light to get out. All of that mass condensed in a very, very dense region. Any guesses? Mile. A mile is a good one. So it turns out there's a fun equation for it. I did the math, so you don't have to. That's the whole point of having grad students. And it basically is directly proportional to the mass of the object. Then c squared is, c is the speed of light. You've probably seen the quantity c squared from Einstein's relativity equations, E equals mc squared. This is just the escape velocity equation for any object with the speed of light plugged in. So about 4 miles. So if the sun was a black hole, it would fit in between like Ferndale and Royal Oak, just about. Very, very small objects. So as you can imagine, it's very hard to find them out in space. This is not a large object that is emitting a lot of, size. The best way to find them, as it turns out, is going to be through their interactions with space, with light, and with other objects. So here's a really great example of what black holes do to light. What we're going to see here is a simulation of 2 black holes. These have accretion disks. Those are that spiraling material that falls towards the black hole gravitationally. You can see the photon spheres here. I'll turn you down just a little bit because you're a little bit loud today. So there's those photon spheres again. And now we're going from a top-down bird's eye view to a straight-on view. The accretion disk is still in the same plane as us. It's still parallel to us. But the gravity around the black hole is so strong that it's trying to bend the material towards it. This light is basically trying to get pulled into an orbit the same way that material orbits the sun. This was actually a consequence of general relativity that Einstein discovered back in about 1919 during the eclipse. It turns out that our sun does this as well. He observed during an eclipse the width of the Hyades cluster in Taurus the Bull and saw that it had shrunk a little bit. It had actually bent around the sun and gotten a little bit narrower. And similarly, we can see gravitational lensing, this effect of gravity quite literally focusing light from behind an object to the front, forming a lens in galaxies, and we've actually begun to observe it in black holes as well. I'll show you the final image of Messier 87 that was taken with the Event Horizon Telescope later on during the talk. But I think now is a great time to actually pause for questions. Does anyone have any questions before we get into kind of the physics of what's going on with that gravitational lensing?
So I thought that during that solar eclipse that they were looking at a star that was also behind it. I guess they were looking at the Pleiades, but I thought for some reason I remembered it being Regulus or something that was behind the sun, but then they could still see it.
Yeah.
It was curved. So
So
you're saying it's the Pleiades that they were looking at.
The Hyades specifically. So Regulus is in Leo. Regulus is a couple of zodiac constellations away. He was specifically looking at Taurus, and Taurus is on the ecliptic, right? You have like your April, your March, and Taurus has this beautiful cluster.
Yeah.
And Aldebaran is like this bright red eye of the bull. And so the Hyades usually has like a pretty open angle to it. And then when you put the sun in front of it, these stars, you're right, there were some stars that were like kind of supposed to be behind it, right? The Hyades is a much more amorphous blob than I've drawn. There are stars that are supposed to be behind it that get lensed to the front, and it gets kind of this waist cinching effect in the middle of the cluster around the star. Yeah, great question. So what this kind of proved for the first of many times is that matter bends space. The classic example in a three-dimensional framework rather than a four-dimensional framework of space-time is sitting on a trampoline, right? You're sitting on a trampoline and somebody rolls a marble towards you. The marble is not going to go on the straight path that it would have gone if you were not there. You're literally bending the fabric of the trampoline under your weight, and so things are going to start to curve towards you. So for an example, here we have our sun. You can see that it does bend space nearby the face of the sun. Really cool effect of this is the precession of Mercury. So Mercury's orbit is elliptical, and it does this kind of spirograph shape over the sun over the course of each of its orbits, right? Its orbit is about 88 days. And each time it ends up at aphelion in a different part of the solar system. And this is because it is experiencing this kind of relativistic dragging where it's like getting disrupted in its orbit and it ends up getting flung out to a different part of the solar system. So there have been really, really robust tests of general relativity around stars for a very long time. And then in around the 1960s, you start to get people saying, okay, so what happens if the material gets more dense? Let's put more density on there. And they realized that the math shows you that eventually you'll get like a divide by zero error, right? Eventually the radius becomes zero and the gravitational force becomes infinite. And so this becomes the singularity. And you can tell that this idea wasn't taken super seriously because it doesn't have a very scientific name. It's just, what if we made a black hole, guys? And then we start to see observational evidence of these, as you'll see. So a lot of the times people ask, what is inside the black hole, right? I'm a physicist, I should know this. We don't know. So like I mentioned, light travels at the speed limit for our universe. It turns out gravitational waves travel at that speed limit. Neutrinos travel at that speed limit. Cosmic rays, which are just particles, travel a little slower than that, right? Everything we know to get information from is going to be trapped inside of this singularity. Once you get to this event horizon, you can see that the gravitational light bending is still pretty extreme before you get there. That's why we see things like the cool photon sphere. That's material that's trapped down in this part of the gravitational potential well. But we don't know of anything that can support a physical surface at the densities that we need to make a black hole. Neutron stars, like I said, that's the densest thing we know of. And we're not even sure exactly how the equation of state works for that. We don't really know where the pressure comes from. Things like NICER, the primary goal of NICER, as well as things like LIGO, the Gravitational Wave Observatory, they all work to try and understand things like this, because that might give us some information, right? Maybe there's some mathematical quirk that we can figure out to try and understand what's going on inside the black hole, similarly to how we figured this out from a mathematical quirk from general relativity. Now, we just know that it is spherically symmetric because we see things orbit it, and gravity, the material is still exhibiting a spherically symmetric gravitational field, right? Those accretion disks that we saw all look like nice little rings. But other than that, we don't know. There are ideas that maybe it pops through to a different dimension and goes out somewhere. I personally disagree with that because we see black holes growing over cosmic time, right? But it's an interesting idea. And I wouldn't be someone to definitively disagree with anything about what happens inside of a black hole because we just don't know. Does anyone have any questions about that? Yeah, Dale.
One thing, I think, if I understand correctly, it's possible to measure not only the mass of the black hole, but how fast it's spinning.
Yeah.
When a black hole spins, does it bulge at its equator?
Good question. We do not have the requisite data to tell what the shape of the black hole is around the equator. We can almost start to measure their spins. The way that we do this is actually with something called X-ray reverberation mapping, which is very close to my heart. Basically, you can measure the innermost stable. I'm going to erase Mercury. Mercury's done. We've moved on from the solar system. You can measure the innermost stable circular orbit of a black hole. So here's the event horizon, and then here's the accretion disk. You can use this technique called reverberation mapping to measure the masses of the black hole. Basically, we know how things in a Keplerian orbit move. We know the relationship between their period and their distance, and then the central mass of the object. And it turns out that around black holes, in addition to this disk, there's this thing called the broadline region, which is this free-moving relativistic gas. I'm so excited to come here. I knew you guys were going to ask really good questions. And you can measure the distance between, let's say, the UV emitting accretion disk. So this is emitting in the ultraviolet. Let's stick with the optical. Let's keep things simple. Let's say it's the optical. Let's say this is the R band for photometry, right? You're doing some R band photometry. And then you see an emission line that is also peaking in the R band. And you see this X-ray flare. And one day after the X-ray flare, you see a flare in your R band. This is just light emitting and irradiating the black hole.
People don't know what an R band is.
Oh, okay. I wasn't sure how much like photometry. Basically, you break up the EM spectrum, right? You have your Roy G. Biv.
Yeah.
It's similar to like an H alpha filter, right? If you just take a filter that only cuts out this one part of the object, you'll be able to see the variability of just the part of the black hole's accretion disk that is emitting in that wavelength. Does that make sense? And so if you have different colors of the black hole or different colors emitting at different radii from the disk, you can kind of get a distance measurement. So what they do is, this has been done since the 80s by some of the people in my research groups. They'll measure the distance between a flare in this part of the black hole, just with time, and then a flare in this free moving gas from some H alpha line or something like this. And of course, the filters are a little different than what we would use for regular H alpha because these are crazy redshifted galaxies. But if you say that this takes 1 day, and then it takes 30 days to get to your broad emission line, that tells you that there's a distance of 29 light days between these two regions. And you can also measure the speed at which these gas is moving. It's orbiting the black hole. You make that assumption. It seems to work out quite well. And then bada bing, bada boom, you now have the radius to the black hole, and that tells you the mass of the black hole just from the virial motion, assuming like basically that the object is moving in kind of a Keplerian orbit. So that's how we measure the mass of the black holes. And then from there, we can also measure things like the spin of the black hole by saying how close is the first signal that we get from a black hole accretion disk? Is it here or is it a little further out? The further out it is, the slower it's spinning. And then if it's spinning really rapidly, the black hole will be able to move forward in time. It'll be able to move forward closer to the black hole without getting disrupted. This is something called relativistic frame dragging.
I was going to ask if frame dragging ever came.
Yeah, absolutely. And so the reason that we care about the spins of the black hole, if you're not interested in the minutia, is that we have a few different ways that supermassive black holes might grow over cosmic time. They can either be fed predominantly by accretion, that is material kind of slowly spiraling into the black hole, or they can be fed by mergers, where you have multiple supermassive black holes, either in early primordial universe time around the emission of the cosmic microwave background, or through galaxy mergers. And this is a very coherent, clean process. This is material kind of gets caught in the orbit of the black hole, processes inward, you have that relativistic effect. And just like how most of the things in the solar system are orbiting in a prograde orbit around the sun, the accretion disk is going to be moving prograde, and it's going to spin up the black hole. Some of this angular momentum from the disk gets imparted onto the black hole, speeding it up. So you would expect that we would see more of these innermost stable circular orbits near the black hole surface. If it's a bunch of mergers, then it will kind of disrupt the spin of it, right? They're all going in different directions and you end up with a lower spin. So we would expect to see ISCOs or innermost stable circular orbits farther out. This is something that the next generation of space telescopes, XRISM, that just launched, the X-ray telescope, this might be able to track some of these and try to come up with a better answer for what the spin is. And then there was a question back here, and then I'll come back to you if that's all right. Perfect. Yeah, what was your question?
Well, you're not a big fan of it going into a wormhole?
No, again, right. We know that there's material in the black hole because things are orbiting towards it. And if these black holes are growing over cosmic time, which they seem to be doing, for instance, Messier 87, the largest black hole in our part of the universe, is the result of merger after merger after merger of galaxies. And so it looks like those black holes are associated with every major galaxy that we know of start to merge together and become larger. I think if that mass was leaving somewhere else, it's unlikely that it would be able to hold space in the configuration that it has, right? The sun bends space a little bit where it is right now. And then when it goes somewhere else, that part of space will be relaxed, just like if you walk to a different part of the trampoline. So I think because the black holes grow over cosmic time and are associated with these larger and larger galaxies from the result of mergers, we do know at least some of the black hole growth comes from accretion and some of it comes from mergers. It's never black and white in astronomy, but because we see these merger remnants that have these really massive black holes, I think the mass has to stay down there. It's a great question though, but that is of course more speculative. So I would invite someone to prove me wrong with some sort of scientific experiment. Dale, and then I'll, yeah.
Okay, this is probably naive, but with elementary particles, the way you learn about them is you smash them into each other, right?
Yeah.
Our gravitational wave detection equipment is getting better and better. And sooner or later, we're going to have a black hole, either a neutron star hitting a black hole or two black holes merging close to us where we can get high resolution data with good signal to noise ratio. In the moment of collision, it seems to me there's at least a possibility that we might see some hints or data on what's inside a black hole by the way they collide.
Yeah, the tidal deformability parameter is what it's typically called, like how much it will deform from a spherical shape. I agree with you that we don't have the sensitivity yet, but I would also not be surprised. We do that with neutron star mergers. I'll talk about this a little more later in the talk because actually to go into LIGO stuff. That was my undergraduate research, was gravitational waves. So I'm very excited about those as well. We'll talk a little more about how gravitational waves work so that everybody is kind of aware. And then I can talk a little about the tidal deformability. But that's a great question. Yeah, absolutely. Over here.
Yeah, I was just wondering about something. Black holes we're talking about are made up of matter as a result of normal matter condensing into this. Has there been any thought or talk about the possibility of dark matter forming black holes?
There absolutely has. So when we go into this question of do black holes merge or do they accrete, one of the big things is we know that there's a ton of dark matter in the universe, and we actually have seen from perturbations in the cosmic microwave background that some of that has to be due to gravitational instabilities from dark matter. When you look at the cosmic microwave background, right, you see the little hot and cool spots. And they're by millikelvin. It's very, very small amounts, but you can't explain that with the gravity from the observable universe's matter. So we know there has to be dark matter. And we are pretty sure that some black holes formed early in the universe because of these collapses before you could even get to a star phase. There was just too much material. So the general consensus among scientists is that absolutely some of the matter in these black holes, especially the early ones, is going to be dark matter. We don't have a great way of observing it because most of the only way we can observe black holes is through light and interaction with visible matter, but the idea is definitely there.
Well, if you see a star going around, something that's invisible.
Precisely, and we haven't seen anything that's invisible that wasn't a black hole yet. It's a great question.
So what comes after black hole?
Yeah.
Get bigger and bigger.
More black hole. There's right, this material is literally stuck in here by all known laws of physics. The other thing that we think about, the other reason that I'm a little skeptical of the white hole wormhole thing is if material was coming out of a black hole and going somewhere else, it would have to be going so fast, right? This thing blows in the X-rays right before it falls in. We would see these huge streams of high energy particles around the universe from white holes coming to us, right? Unless there's fundamentally something special about our universe that we only have black holes going out and nothing is coming in. That was one of the major motivations of the early 2000s, these huge X-ray surveys of the sky was, do we see any sort of X-ray emission that we can't explain by stuff near the event horizon? And none of it is moving fast enough to be coming out of a black hole. It's just moving at the right speed to go into a black hole. So that kind of whole field of thought got kind of dampened at the very least. Yeah.
Primordial black holes, yes
Mhm.
or no?
Yeah, I think so. That was kind of what I was talking about with the dark matter question. So those primordial black holes are just what might have seeded the supermassive black holes. I think so. Again, I don't have the spin measurements to tell you, but hopefully within my career and my lifetime, we will have more to say about the relative fraction of growth through primordial black hole mergers. Basically, these black holes are millions to billions of times the mass of the sun. And we don't have a great explanation for why they get there through just black hole star-sized black hole mergers, right? It's very hard to get a bunch of black holes to merge because they tend to have a lot of gravitational kick. And in most simulations of black holes merging, one will just try to throw the other one out of the galaxy. So the idea that while everything was really close together, these really large black holes formed is the primordial black hole theory. I'll keep moving for now, but I will definitely take more questions. So we've talked a little bit about this, but I want to show you a cool visualization. This is your star collapsing at that last moment in a supernova once it's tried to produce iron, failed to fuse it, and lost all of its radiation pressure. Then what's going to happen is the remnant neutron star that is held together by that neutron degeneracy pressure will emerge in the former core. And for stars about 20 solar masses, it's pretty much guaranteed that you're going to have too much stuff in the center to support that neutron star. So it's going to collapse inward and become a black hole. Now, there's still material falling towards the black hole. Like we mentioned, it makes that accretion disk. And you can see this very short-lived and very short-lived after supernovae, potentially. Again, our observations have not gotten fantastic enough to detect supernovae before at the time scales that happens. But as our time domain surveys, things like Assassin and other time domain monitoring projects get better, that's always the hope. Space telescopes would be what you would need for an X-ray source to be observed. So things like Castor and Ultrasat and all these various space telescopes that I'm happy to talk about are kind of designed to be able to catch those early moments of a supernova and try and observe that material. We don't really know exactly the mass that it takes to form a black hole versus a neutron star. You have to be at least 8 solar masses to form a supernova of this type, form at least a neutron star. And then we say once you get around 20 solar masses, it's pretty likely to form a black hole. Betelgeuse and Rigel and Orion, the shoulder and the foot, those 2 bright stars, those ones I would say like maybe would form a black hole. They're around 15 to 16 solar masses. So the first black hole that was ever discovered, I mentioned briefly that in the 60s, astronomers start talking about like, whoa, what if we collapse stuff even smaller than the sun? What happens to general relativity then? And then in 1964, this weather balloon with an X-ray detector that was actually looking for X-ray radiation from nuclear testing on Earth did a sweep of the sky, looked at the constellation Cygnus and went, what is that? This is the brightest X-ray source in the sky. And so the astronomers who had just been trying to figure out what would happen to material near this black hole that they had invented are like, we need to do the math. And by 1971, there is this really, really solid body of evidence. The X-ray emission that you see from this X1 X-ray source is very consistent with what theorists predict is passing across the event horizon of a black hole. It would emit these intense X-ray radiation as the disk breaks up, and you just get this plasma of free electrons. We call it the corona, similar to the sun's corona. Similarly, not very well understood as well. So somebody asked about things observing an invisible object. What the final result for why this was a black hole was actually observing its binary companion. And if you look at the radial velocity of this thing, it gets Doppler boosted and then Doppler dragged. It starts to speed up and slow down like it's orbiting something, but there's no thermal signature for a star. All there is this crazy X-ray source, and it's orbiting way too close for it to have this nice circular profile. From the motion of a star, you can kind of see if it's been stretched out, if it's starting to get like tidally ripped apart. It's a very nice star with just a little bit of a tidal lobe. And the only way that you could explain the dynamics of this system is a black hole and star companion. So we call these black hole X-ray binaries. This is the first one that was discovered, and there have been dozens more in our galaxy that have been confirmed. This is kind of a rare state in the star's life, right? This is, while this star is has to be quite large, it has to be in the end of its lifetime, so it's expanding, and then that material starts getting funneled gravitationally onto its black hole companion. We know that about 50% of all stars in the galaxy, at the least, were formed in a binary system. And so this was some star that went supernova, resulted in a black hole, and is now kind of draining the life force from its companion and speeding up the mass loss of this star. So these two will have a very interesting cosmic evolution. This one is now losing mass, so it's going down the mass function, and it's probably going to have a way less dramatic death than it would have initially, because some of that mass is going to its companion. So this mass of the black hole is about 14 solar masses. This was something very large that is now stealing mass from its companion. But this, again, is not near the millions to billions of solar masses that we see at the galactic centers of large galaxies. So we'll get to those in a second. That's where we start to think maybe there's more than just these successive mergers of Cygnus X1 type black holes. So if you can go outside and it's not too cloudy, you can find the constellation Cygnus. I'm sure we're all familiar with the neck of the swan. We have the tail feathers, we have Alberio, and then near Eta Cygni, this is where Cygnus X1 lies. Now, I'll ask you all a question. You're astronomers. Can we see the X-ray source from a telescope on the Earth? No, why not? Yeah, so the HD, what's the companion star's name? Yeah, HDE 226868. Yeah. This was discovered with a ground-based observatory. So if you had a good telescope and good observing conditions, that one would be available. It's just a very faint star, and you could totally try to track the radial velocity profile of it and observe that binary motion. I don't know what the specs would be for what you would need, but this paper, you know, if you look for the original paper for this, you could just replicate what they did for sure. We can't see the X-ray source, and this is because of the Earth's atmosphere. So the best and worst part of my job are this X-rays can't penetrate the atmosphere, right? I'm alive. I haven't been irradiated by like space X-rays yet, but also there are about like 5 X-ray telescopes in space that do what I need them to do. And so all of the X-ray astronomers are all competing over these few telescopes that are in space. We can't just go build our own X-ray detector because you can't see them on Earth. That's why it took until the 1960s on this weather balloon to even discover Cygnus X1 in the first place. But those X-rays, that is all my thesis, is just trying to understand what drives that X-ray variability that we then see the signature of outside in the outer environment of the black hole. So again, a little bit more zoomed out. Here's Eta Cygni. It's kind of in the center of the summer triangle. So I always try to look for it. Just a little pay respect to the historical black hole. So we had a question about gravitational waves. This is what we think will happen in a system like Eta Cygni eventually, if that other star forms a black hole. You have these 2 stars that formed together, and they, as they get closer and closer together, begin to emit energy in the form of gravitational waves. Much like a boat going through a river has to input some energy to just get through space, right, to create that wake. If I'm moving something extremely dense and it is warping space-time, as I move it, it's going to create a gravitational wave. It's going to stretch and squeeze the fabric of space same way we've talked about with light bending. And that's going to take a little bit of energy. So walking across the room, you don't substantially bend space in any way, but something with the density of something like Cygnus X1 absolutely will. So what's going on here is as they get closer to each other, you can see that the ripples start to become stronger. They're moving faster and faster. And so they're losing their energy much more rapidly. And what's going to happen is eventually these gravitationally bound objects are going to run out of orbital energy and collide inward. There's going to be this really dramatic peak of gravitational wave that goes out as the merger happens. And then there's what's called the ring down, where they start to merge together. That ring down signal, that's where you would potentially get any information about what's going on inside of the black hole. We don't have the sensitivity to it now. And the reason for that is that we are kind of limited by a lot of things here on Earth. So show you what the gravitational wave detection looks like. So imagine, if you will, that you are a ring of test particles. This is what they teach you day one as an undergrad at LIGO. You're a ring of test particles. It's just we built a hula hoop. Why not? And as the gravitational wave passes by, first it's going to stretch your hula hoop, and then it's going to squeeze your hula hoop, stretch and squeeze and stretch and squeeze. And then as that ring down happens, it's going to happen extremely rapidly, and the stretching is going to get way bigger, right? It's a really good way to get in your arm stretches. And what's going to happen on Earth is that all of us are constantly being stretched and squeezed by these gravitational waves. But all of you and all of the room and everybody around you is also getting stretched by the gravitational waves. So from your frame of reference, you don't see anything different. Light, on the other hand, moves at the same speed, regardless of what space is doing. All it cares about is how fast those electric and magnetic fields can dance with one another. This is the concept of special relativity. Basically, light is always going to move at a constant speed, regardless of the speed of the thing that it was launched from. And so some really cool astronomers, Kip Thorne was one of them. He won the Nobel Prize in 2015 for this. This was like, yeah, absolutely. He was the science consultant for Interstellar also before he won the Nobel Prize. He had the idea for this experiment in the 80s, and it took until 2015 for the first successful detection because it is so hard to tune this laser. Basically, what happens is you send out a laser beam, you fire it along two axes, you split it in half, fire it along 2 meters. These are 2 arms. These arms are about 4 kilometers wide. One of them is in Hanford, Washington. One of them is at Livingston, Louisiana. They're the exact same setup. And so that light beam gets split up. It comes back in phase. The mirrors are tuned so that the distance is equivalent to each other within one wavelength. So then the light comes back in, it recombines, and you get a perfectly reconstructed beam. Now, as gravitational waves pass by, they're going to, like I said, stretch and squeeze and stretch and squeeze, and they pull the light in and out of phase with one another, corresponding to the strain that's put on the detector. Strain is the word that the LIGO people use, just how much those arms are being stretched and squeezed. And this happens within milliseconds. So you have to have a very, very fine-tuned optics sensor to try and figure out how much that light is blinking, the right distance between each of these blinks, and then the amount of time that it takes, right? Well, the amount of time that it takes will tell you how far along the arms get stretched. And so that will tell you what the strain or the gravitational wave amplitude was, as well as how often these peaks happen. That'll tell you the frequency of them. So then what you get is this famous plot that came out in 2015. And the reason that they have 2 detectors is because, as it turns out, there's a lot of things on human Earth that will also cause these detectors to wobble. So notoriously, I remember going into a meeting and one of the grad students, his job was to figure out the train schedule for Livingston, because they had built a train line that runs right next to the detector, and a train comes by and it produces a gravitational signal. There's a logging yard that also, a tree falls, that produces a signal. And so you have these 2 things on the opposite sides of the country, and you have to see the same signal, right, hit Hanford, and then the light travel time of light between Hanford and Livingston. After that, you should see the exact same signal hit Livingston if it's coming from this direction in space, or if it's coming from this direction, you would see the opposite. There's also Virgo in Italy. Right now, you've got kind of a triangulation you can do. You can figure out the speed, or the speed is always the same for the gravitational wave. They turn out to propagate at the speed of light as well. But you can figure out the direction, right? If it hits Virgo first and then kind of passes in a circular wave front out, you can end up reconstructing the source of it based on the number of detectors you have. There's also LIGO India, which is trying to get built. And basically, the more detectors we have, the more statistical confidence we can say when a gravitational wave passes through. This one was a pretty loud one. This was a 36 and 29 solar mass black hole. This was GW 150914, so 2015, September 14th. It's just always the date. And my advisor had this picture on her billboard outside her office, because this was one of the first direct proof of gravitational, of general relativity affecting things in the regime of a black hole. We actually see black holes stretching and squeezing space. Neutron stars do this as well. GW 170817 was the one that I was working on. And these were 2 neutron stars. So these are that kind of very dense, compact matter, but they actually get a little stretchy. They get a little ooey gooey as they tidally deform. The gravitational forces on the near sides of the objects rip one another apart. And that tells you things about, for instance, the neutron star equation of state. If we can ever get this post-merger signal with any precision, you can see that the post-merger signal becomes kind of a mess. Now you're in the regime where optical noise and all sorts of stuff get all messy. So you can kind of triangulate their source using the multiple detections. And then as you approach the black hole, if you were matter, kind of spin things in a slightly different direction, you would get spaghettified. I always like to include this because I think this is one of my favorite terms from astronomy. Basically, as you get closer to the surface of a massive object or the center of a massive object, your gravitational acceleration increases, right? The gravitational acceleration that the moon experiences is a lot less than it is here on Earth. That's why, for instance, the moon orbits every 28 days and the International Space Station orbits every 90 minutes. They're both trying to avoid falling into the gravitational infall of the Earth, but the moon is much farther away, so it gets to do so at a much slower pace. As you get to a black hole, the difference in gravitational acceleration between the lower half of your body and the upper half of your body is significant enough that your feet will start to get accelerated away from you. And this happens near the event horizon, right? This is where that gravitational warping becomes so strong. And then, of course, move forward a second later. Now the distance between your head and feet is even longer. So the acceleration kind of multiplies on itself and you end up stretched out into this tube where your feet are just getting accelerated away faster and faster. Of course, you know, we haven't been able to travel to a black hole yet. So we don't know what this would do to the human body, but the math works out and it's consistent with the kind of strong gravity that we see around these X-ray measurements of black holes. The other thing that happens is that time will start to change, right? Your perception of time depends on how much gravity is around you. This is another one of those Einstein gravitational general relativity consequences. And so let's say this is Interstellar is one of my favorite movies. It came out right when I was applying to college, and they actually play with this a little bit, right? Let's say that you are in a spaceship and your friend needs to dive into the black hole. If you watch your friend, they are going to appear to slow down as they get closer to the black hole. And from your perspective, you're accelerating just like you normally accelerate under gravity, right? You go up and then you start going down really fast. And everything around you in the non-relativistic frame of the universe starts to age really quickly. Your space mate just disappears. Galaxies start to move, the stars start to move, everything happens extraordinarily fast. And we know that this happens because it happens to us even in near Earth orbit. Can anybody think of an example where this time dilation would be relevant?
Yep.
Precisely. So clocks run a little faster in low gravity. So the ISS, all of your GPS satellites, they have to account for some sort of time dilation effect. And the farther you are from the Earth, the more strong that effect is going to be. So this is something that ends up getting taken account for even in near Earth orbit. So this would be something that gets very extreme, and the dilation is much larger than 30 microseconds per day as you approach the black hole. That's exactly right. So the last couple of examples that we have for how scientists are using black holes to study kind of stuff all around the universe. The first one is our detection of Sagittarius A star. So Sagittarius A star, much like Cygnus X1, was detected kind of indirectly in electromagnetic wavelengths. Carl Jansky, the father of radio astronomy, found this in 1931. Turns out you can do radio astronomy from here on Earth. And then it was confirmed to be a black hole by Andrea Gheze's team. This was the second Nobel Prize in black holes in like 5 years. It's like ridiculous. It was a great time to be an astrophysicist. And what Andrea's team discovered was that this S0 star here, you'll see it moving. Which one are you? Oh, there's S0. It's the yellow one. This distance here, you could not fit all of the mass that it is orbiting around with stars. It would crash into all of the stars. The only thing that could get that close at peri-Astron or peri-Blackholian would be a black hole itself. So that was her Nobel Prize, and she'd been working on that, you can see, since 95 to 2011, and it was finally verified enough to get the Nobel Prize in 2020. You can see that one kind of pouring out of the teapot of Sagittarius. And then the other thing that we see is that Sagittarius A star was not always this quiet, nice little quiescent radio source. There are these huge X-ray and gamma ray bubbles above and below the plane of the black hole. And this tells us that our black hole was once active. It was once putting out all those X-rays and gamma rays, the same way that Cygnus X1 is doing at a smaller scale, and the same way that about 2 to 15% of other galactic black holes, depending on which scientist you ask, the surveys are kind of incomplete. But about 2 to 15% of them also have this active emission. And the crazy thing about this is that I mentioned way earlier, in order to form a star, you have to have very cold molecular gas. If your black hole is just throwing X-rays out into the center of your galaxy, that's going to heat up your gas and slow down star formation. So when we think of things like how much life is there in the universe, how many other habitable planets are there, you have to account for things like feedback from black holes. So that's where my research really focuses. This is another one of the greatest black hole achievements that happened during that very short time. This one I don't think will get a Nobel Prize, just because it's an observational thing, and I think the timing is really bad, but you never know, they might get one eventually. But this is the radio interferometer setup. So basically they use over 30 telescopes all around the Earth, simultaneously monitoring this black hole. And it turns out that if you construct the differences in the line of sight from all of the telescopes, you can actually figure out where it's brighter, where it's fainter. I like to say my cheap X-ray astronomer heuristic is it's kind of like if you put your finger out and then you close one eye and open the other one and you see your finger kind of looks different, right? If you have eyes all over the side of your face, and you piece together that image, you can kind of get a 3D replica of your finger. Similarly, they can construct this image of the black hole through a bunch of observational radio data. So this is an observational image of a black hole. It's just taken by combining several different radio astronomical cameras all over the place. And you can see here some of the gravitational effects. We have this Doppler boosting. This part here is the part rotating towards us. That's why it's so much brighter. Here's the part away from us. And you can kind of see the like halo of the gravitational lensing as well. So I was talking with Dale about this a little while ago, and we were talking about how this was exactly like what the simulations predicted light around a black hole would look like. So general relativity, special relativity, both really work, folks. And this is the largest black hole in our nearby neighborhood. This is in our and in the Virgo cluster. And this is 6.5 billion solar masses. This is that one I was talking about. Must have come from multiple mergers of different galaxies, because the galactic host of this M87 has remnants with chemical compositions of at least 2 or 3 different galaxies that have all been kind of swirled together. So this is the setup for the EHT. You can see they've got telescopes all around the world on one half of the Earth, and they all simultaneously observe it to construct that image. It's visible in the Virgo cluster. It's in between Virgo and Leo in the spring sky. And this relates to what I do with my research, actually. So I am very interested in the impact of those black holes and how they affect their environment. It turns out they kick off winds. So you see that there's this heated wind. We think it's kind of maybe powered similar to the solar wind, where you have magnetic reconnection, spitting material out. And I use NICER, which is this little instrument aboard the International Space Station. It observes very rapidly. This is like 1,000 times sped up version of this. So it takes these 1,000 second observations for me pretty much every day. And we use that to track things like how the X-ray flux from the center region near the black hole impacts this wind. Is it accelerating it outward fast enough to reach the rest of the galaxy? So I have a paper that I worked on with some of the scientists at the Hubble Space Telescope. NICER and Hubble simultaneously tracked this wind coming off of a black hole for, it's been going on for about 1,000 days. My data is coming in a little faster, the analysis part, rather than the Hubble. Hubble guy is not a grad student, so he doesn't have a timeline for this, but he's got the first year of it. And we see these huge clumps of material that are more dense by a factor of about 10, changing the obscuration that we see. So we see these giant clumps of wind, kind of like in that artist's impression. About every 100 days or so, they fly up across our line of sight, get disrupted, and then a new one flies up, another one flies up, and then now we're in this state where the X-rays are really bright and it looks like the clumps have been totally disrupted. So the physics we're trying to do now is figure out what effect those winds will have on the interstellar medium, and if they will actually be able to do things like stop star formation and potentially enrich the solar system with the universe with heavy elements, because you get supernovae and stuff happening in the disks of these materials. So there might be things like iron that would not be formed otherwise in high quantities. So yeah, there's my paper if anyone's interested in some reading before bedtime. It's kind of a cool study, but I won't go into it too much. The last thing that I'll show you all is just kind of what might happen to our galaxy in the future. We talk about galaxy mergers potentially leading into these active galactic nuclei as the black holes in the centers of these galaxies plow through towards one another. So the black hole of the Andromeda galaxy was measured with a pretty similar technique to the one that we did with ours, where you observe these stars moving around the black hole. Now, we don't have as much precision, so we're off by a factor of about 1 here. But we think this is about 5 to 10 times more, about like 50 to 100 times more massive than our own supermassive black hole. So it might be very similar to that schematic we showed at the very beginning, where the one large one and small one kind of orbit around one another. We all hopefully know where to find the Andromeda galaxy in the constellation of Andromeda. It's the only galaxy that can be seen with the unaided eye from our hemisphere. It's so beautiful, and it is moving towards us. So there's been a recent, the number was 4 billion years from a Harvard study in 2012, tracking its radial velocity. Now the recent update, I think, puts it at about 5 billion years. But basically, within our little triangle of galaxies, we have Andromeda, we have Triangulum, and we have Milky Way. Andromeda and Milky Way are moving towards each other such that they will get gravitationally captured and begin to merge in about 4 to 5 billion years. So here's what we see now. Yeah, not while the sun is even doing what it's doing right now. This will be around when the sun turns into its late stage red giant phase. But this beautiful simulation puts together what it's going to look like at these billion-year timestamps. And so what we see is that first Andromeda is going to get very, very large. And then the tidal forces, right, the gravitational interaction from the arms that are near each other are going to start to pull on each other. And it's called a merger, right? It's not a collision. The odds of any two stars actually bumping into another are like less than 1% of 1% of 1%. Space is very empty. It's going to be a little bit more like shuffling a deck of cards. Everything is going to get kind of collated together. The arms are going to go all crazy for 1 billion years or so. And then the sky is going to be much brighter than it was beforehand, because we'll have the combined stars from both galaxies. During this time, it's likely that the black holes will get some material around them and they will become active. We've seen signatures of these dual active galactic nuclei in other galaxies. And so that might also sort of trigger this new era of heating and reionization of the galaxy. Finally, we'll end up with this very beautiful, bright elliptical galaxy that will be the Milk-Andromeda galaxy. So that is it for me tonight. Hopefully you've learned a little bit about black holes and how they form, how we observe them. And the last thing I'll leave you with is we are never going to fall into our black hole, at least before this Milkdromeda thing. I got into this because I was scared as a child that we would get eaten by the black hole. Just like we're not going to fall into the sun, we're in a very circularly stable little path around the Milky Way. So we're going to be fine. I can't say what's going to happen when this merger happens, but fingers crossed. Yeah, thank you.
Led you to this career.
Exactly. Yeah.
Wow.
I just started learning everything I could about black holes and then applied to grad school and they were like, you know a lot about black holes. And I was like, thanks. Yeah. I know.
Did you go through an amateur astronomy phase?
Yeah. So I was never great with telescopes, actually. I would get very impatient. I always admire people. I think Adrian has seen me at Belle Isle. I tend to get very frustrated with the telescopes.
We have to go over there, Jeff and I, Jeff's not here. We have to go set it up.
Oh yeah, it's so it's a rough one. It very much is. I was very much the reading astronomy magazine type of kid, and I learned some of the constellations. My first astronomy job was actually, this is my strength. This is what I usually do when we go out there. I know most of the constellations and I know the cool deep sky objects. So I can be like, there's a black hole there. You can't see it, but it's there. So that was kind of my amateur astronomy phase, was looking at star atlases and identifying them. And then I think that's maybe why I got into space telescopes also, is because I continue to not as I've gotten older, I've really enjoyed, my partner has a Dobsonian. I love working with that. But my amateur astronomy phase was very much reading and pointing out constellations and less so telescopes. So it's always something that I admire, seeing people, at like astronomy at the beach or at the Belle Isle event, just rapid fire observing all of these deep sky targets.
Is there another one coming up at some point?
Great question. We didn't end up having one in October. I think the eclipse, they ended up doing stuff during the day for the eclipse instead. But I'm hoping we'll have one at least in April before I leave. But I think that they're kind of losing momentum on that. So I'll keep you posted.
Okay.
Yeah, great question.
Good job.
Yeah, thank you. I appreciate all the questions in the middle. It's always a nice break from the talking. All right. Yeah, take care. And then I have a business card. I'll put it over by the snack table in case anybody has questions they want to email me or stuff about space telescopes in general. And yeah, thank you all so much for having me. This has been very fun.
Okay. So jump here. Okay, that's a wrap. Thanks everyone for coming. Our next star party and open house is at Stargate Observatory on October 28th. Our next meeting is in person at Cranbrook, Monday, November 6th. We're having elections then. And we're going to meet afterwards at the National Coney Island on Groesbeck, just south of 12 Mile after this. Clear skies, everyone. Good night.
I don't know if they're still doing it. I think they might have just finished, but have you seen a play Silent Sky before? Wayne State was doing it. It is this play about one of the first big female astronomers. Her name was Henrietta Leavitt, and she was the person who discovered this standard candle that led to Hubble discovering things like the expansion of the universe. I watched it